we'll record the rest of this. So again, this is how we would solve the root mean square equation that I showed on this slide. How to solve for the speed of one individual gas. Now, the next topic is instead of one gas, what if we have two different gases together? In biology, you learned that diffusion is something going from a high concentration to a low concentration. Heck, if you remember the egg lab you did in freshman biology, that was a great example of diffusion. Somewhat similar here if we have a whole bunch of gases and now they're going to intermingle, how they mix together is something that this would show. What I'm going to do is show you an animation that goes over this. So our old chemistry textbook has a very good animation center, and here's a link to it, so if you ever wanted to, you could get to the link yourself of the equation as well. So here's the equation that was given to us. R1 over R2, so the rate of the first gas divided by the rate of the second, equals the square root of M2 over M1. Notice how the 2's and 1's are not on the same line. They're diagonal from each other. The rate of 1 is in the numerator. The molar mass of 1 is in the denominator of the other part. So there's this inverse relationship between them, is what the video mentioned. Again, R1 and R2 are the rate of diffusions. M1 and M2 are the molar masses. There's two ways you could be seeing a problem like this. You could be given a specific rate, like 500 meters per second versus 450 meters per second. That's a rate, how fast per unit distance. Or you could be given a problem that says something like a gas is 3 times faster than another gas. If you say it's 3 times faster, then this could be 3x and this could be x. The x's cancel out. So there's more than one way that this rate aspect is introduced. Molar mass can just be in grams per mole because they're both molar masses. So unlike the previous slide where it had to be in kilograms per mole, not the case for this particular problem. So it could just be their normal molar masses. If, however, time is used instead of rate, we do have to flip it. And I believe there's one question in the web assigned that instead of giving you a rate, it'll say something to the effect of gas A can travel this distance in, or a certain distance in 50 seconds, gas B can travel it in 85 seconds. Notice how the 1's are both in the numerator for this particular one. Again, this is two equations, although usually Graham's law is just referring to the rate one. Two equations that are not given to you on the test for your equation sheet. So I don't know how likely you would be to see them, but I'll give you an example of one that I have seen in the past. So I'm going to skip out of this, and hopefully it won't stop recording again. I've seen a question where it gives you the molar mass of two gases. So one is 80 and one is 20. 20 I would think is neon. 80, I don't know, we can make up something that has a 80. And the question would give you the molar mass of both gases and say how many times faster is neon than the other gas. Some students would do this math and say to themselves, hey, it's 4 times faster because it's 4 times as small. But remember, we got to take the square root of that to equal the rate side of it. So neon, wouldn't it be 4 times faster than mystery gas with a molar mass of 80 grams per mole? Because the square, this divided by that's 4, but we got to take the square root of that still. So it's actually only 2 times faster. That's something I have seen before. Not necessarily using the equation, but you're kind of using the equation. Because again, that equation, R1 over R2 equals the square root of M2 over M1, is comparing two different molar masses, and how do their rates compare? What students should know is that the rates of the two are comparable, but you got to square root when you divide the two. I know I've seen that in a multiple choice before, partly because the numbers work out nice and neat. Remember, multiple choice for the AP exam is meant to be done without a calculator, so there's going to be numbers that just kind of work themselves out. And when they give you something like this, they are begging you to say number 4 times faster. I mean, they're trying to see, do you understand it's actually the square root of that ratio, not just the ratio itself. So that's one way that I will typically see that type of problem delivered, is usually multiple choice, trying to test, do you know it's the square root of the ratio, not just the ratio itself. My last slide. If diffusion is the mixing of two gases, effusion is when one gas is trying to escape. My second bullet point says effusion works under the same principles as Graham's law. What that means is that we could use the same equation. So if gas A effuses at a certain rate, how fast does gas B effuse? Last thing to mention to wrap up notes, and this is probably not something you have to write down necessarily. Helium is lighter than air, and it's a smaller molar mass, let alone the fact that it's less dense. But because it has a smaller molar mass, if I had a balloon filled with helium in the exact same volume of a balloon filled with normal air, and I let it go, the helium balloon would deflate faster. Again, smaller gases move faster, so it can move through that smaller opening faster. That's what that would state. We could actually calculate that using Graham's law if we wanted to.
Is that why helium makes your voice higher and heavy gases make your voice lower?
Helium makes your voice higher because of the density part of it.